All right, hello everybody. So I'm going to go through some of the basics for graphing rational functions. At this point, you know how to do long division and synthetic division, which is going to come in handy when we are doing oblique asymptotes. But for now, what you need to know is that rational functions are functions that are essentially fractions. So you got numerators, you got denominators, and these all look similar, but there are differences depending on the degrees and if the numerator has a bigger degree or the denominator has a bigger degree, or if they're the same degree. But on page 9 in your note/practice packet, this does kind of walk you through step by step what you need to do, and I will highlight some of this stuff and I'll point out kind of what each step looks like in particular, and I may even add a little bit when we start doing vertical asymptotes. And then we'll do, a couple of problems. So let's start with what you need to do first. So first, okay, you need to make sure that you factor everything, numerator and denominator, as much as possible. If anything cancels, then that'll create a hole. Okay? So this is when something cancels. So for example, if I factor out x plus 5, so let's just pretend that we have something like this. Okay? These end up canceling out. And we'll fill in more of the details, but what you do, since x plus 5 cancels out, there's going to be a hole at x equals negative 5. You basically take the factor that cancels out, you set it equal to 0, you got x equals negative 5. As far as finding the y coordinate, then you would just take the negative 5 and plug it into whatever's left. So in this case, if you plug negative 5 in there, here's what we have left. Okay, if you plug in negative 5 into x plus 1, you get negative 5 plus 1, which is negative 4. So then you get negative 1/4. So this would be the location of the hole. And we'll do an example with the hole later on, but that's essentially how you find it. All right, for finding the x-intercepts, okay, you're going to take so in the notes, they refer to the numerator as f of x and the denominator as g of x. Okay? And so right here, when it says let f of x equal 0, you just basically take the numerator and set it equal to 0. So for example, let me write a little smaller now. So let's say you have something like this, x plus 1, x minus 1, and then you got some other stuff on the bottom, x minus 4, x minus 3. Okay, so in this case, you take each one, you set both of these equal to 0, and so you would get x-intercepts of x equals negative 1 and positive 1. In other words, negative 1 comma 0 and 1 comma 0. Those would be your x-intercepts. Okay, to find the y-intercept, you just take x equals 0 and you plug it in and figure out what y is. So just like any other time we're finding a y-intercept, you substitute x equals 0. So for example, let's do a simple one. So here, if I plug 0 into both of these x's, you're going to get y equals 1 over negative 1, which is negative 1. So the y-intercept would be at 0 comma negative 1. Okay. To find the vertical asymptotes, so when they say g of x equals 0, that just means the denominator. So you take your denominator and set that equal to 0. So let's take this example that I have up here. So if we have x plus 1, x minus 1, and then x minus 4, x minus 3, you take your denominator, set it equal to 0. So in this case, you would get x equals 4, and x equals 3 are the vertical asymptotes. And we'll draw an example here in a minute, but I just want to go through all the details first. Next, there's either going to be a horizontal or an oblique asymptote. Okay? And all that means, or how you figure it out, is based on the degree of the numerator. When we have office hours, if anybody wants to see more of the inner workings as far as why these are the situations that we're dealing with, feel free. But for now, I'm going to just kind of keep it straightforward. So first, if the degree of the numerator is greater than the degree of the denominator, so something like x squared plus 4 over x minus 1, okay, this has a degree 2 in the numerator. See how that's a quadratic? In the denominator, it's degree 1. Then there is no horizontal asymptote. There is an oblique, though. So there is an oblique asymptote if the degree of the numerator is bigger than the degree of the denominator. And if that's the case, okay, you do either synthetic or long division and find the quotient. Okay, so you do either long or synthetic division and find the quotient, and that is the equation. This is the oblique asymptote. Okay, and again, we'll do specific problems here in a moment. Now, if the degrees are different, okay, or I'm sorry, if the degree is the same, not different, so something like 2x minus 1, x plus 1, let's say x plus 4, x minus 3, okay? This, if you were to multiply it out, would be a quadratic over a quadratic, okay? Then, and this is kind of written kind of funny. The way I would write it is that the horizontal asymptote is going to be y equals leading coefficient over leading coefficient. So in this case, since it's not multiplied out, you have to imagine, multiply this out. The first term is going to be 2x squared. So for our example, it would be 2 for the leading coefficient. Here, if you multiply the denominator out, you get x squared and then the other stuff. But the key is that the x squared has a 1 coefficient. So in this case, the horizontal asymptote would be y equals 2. Okay, and the last scenario is, what if the degree is larger in the denominator? So let's say you have something like x minus, or x plus 1 over x minus 4, x plus 3, let's say. On top here we have a linear, and here we have a quadratic, so you can see that the denominator has a larger degree. If that's the case, this is an easy case, then it's always y equals 0. That's your horizontal asymptote. Okay? And worth mentioning, so if we jump down to step number 7, it is possible that graphs can cross horizontal or oblique asymptotes, but never vertical. And the reason, again, it's in the packet, but the reason is that horizontal asymptotes represent what's happening at the ends of the graph. So at negative infinity and positive infinity. In the middle of the graph, it could cross the horizontal or oblique asymptotes. Okay. So number 6, we're not going to worry about because I've already kind of talked about how to find the oblique asymptote. And so here we are. So let's just go ahead and talk. Oh, let's add one thing though. Let's go back to page 6 since I'm out of space here on the detailed side. So if you look at page 6 right here where it says find the vertical asymptotes. So let's do a scenario. So here we would have a vertical asymptote of x equals 3. I'm not even going to fill in the numerator. Doesn't matter what's up here. Here we would have a vertical asymptote if you set the denominator equal to 0 of x equals negative 3. Now the difference is what's happening at those asymptotes. So here, for example, if you graph x equals 3, so here's x equals 3 for both of these. Since this is actually a repeated factor, we say the multiplicity is 2. So we count this as a vertical asymptote, but it's counted twice. Anytime we have an even number for the multiplicity, then what's going to happen is one of two things. Either the graph is going to be going the same exact direction and going up on both sides, and then maybe, something like this, or it could be going down on both sides of the asymptote. Okay, so it could look something like this, or maybe something like that, depending on what else we have in the graph. Okay, so that's what I mean by heading the same direction. Now, when you see a vertical asymptote and this exponent is a 1, or even a cubic, anything that's odd, okay? So this example was for even multiplicities. Here we have odd multiplicities. This is to the first power. What that means is that when you graph, here we have a vertical asymptote at x equals negative 3. One of two things is going to happen. On one side, we're going to be heading up, and on the other side, we're going to be heading down. So something like this. Or vice versa. So maybe here, we're heading down and then up on the other side. So opposite directions. Opposite directions if the asymptotes are to the first power or to the third. If it's even, squared or to the fourth power, then you're going to have the graph be kind of mirrored like these. Okay, so that's the background. I know that's a lot of information to handle. I think it'll make more sense as we go through a few examples. So I'm going to start with something like this one. Okay, so I'm going to go through all the steps. We're going to factor, find all the intercepts and all the asymptotes, and then you should be able to graph this without a calculator. Now, you can use the calculator to check, but you should be able to graph without. Okay, so first problem. Already factored, does not reduce. X-intercepts, you look at your numerator, you set it equal to 0. In this case, there's just one x-intercept at 2. The y-intercept, you plug 0 into x, so you're going to get negative 2/3. Vertical asymptote, you look at the denominators. So this is from the numerator. This comes from the denominator. Here you plug in x equals 0. If you take the denominator, make it equal 0, you get x equals negative 3. And I always do write the equation, not just the value, because this is going to be a vertical line. Horizontal asymptote, since the degrees are the same, this is to the first power and that's to the first power, then you're just going to take the leading coefficient, which is a 1 for both of these, and that's going to be 1 divided by 1, and so you get y equals 1. Okay. That means there is no oblique asymptote. Can't have both a horizontal and oblique, it's one or the other. And there is no hole, since nothing canceled out. So now how do you graph this without a calculator? Well, put the information that you have on a graph. So you put an x-intercept of 2, a y-intercept of negative 2/3, vertical asymptote at x equals 3. Oh, I screwed that up already. Oh boy. Okay, so that should actually be x equals negative 3. And unfortunately, I don't have any more whiteout, so we're just going to ignore this vertical line. Sorry about that. Okay, so that vertical line on the right side is not there. Hopefully you guys on your tablet can just erase that, or if you're using pencil for your notes, that's fine. Y equals 1. Looks something like that. And we're good. Okay, so how is the graph going to work? Again, this asymptote is not here, okay? Well, based on the points that I have, I need to see this on the right side of this asymptote, and on the left side, a couple of ways to explain why it needs to be this. Okay, one reason is there are no x-intercepts over here, so it would not make sense to do something like this, because if you did, you'd at some point cross the x-axis as you got near the horizontal asymptote, and you can't do that because we don't have any x-intercepts on this side. The second reason is for what we said earlier, the multiplicity, the denominator here, is just to the first power, so that means that these should be opposite at this asymptote. So one side is heading up and one side is heading down. Okay, and certainly you can check this on the calculator. I would recommend utilizing the alpha y equals feature to get to that numerator denominator template so that you get an easy way to type in the numerator. And I would always recommend when you check these, type in the original equation. So whether it's factored or not, go to the, like for example, if I was going to check number 2, I would factor this, but I would type it in as it is now, before factoring. Okay, and if you hit graph, you can kind of see that we have what we have. Okay, so that's a good way to check. All right, so that's an example of, where there is a horizontal asymptote and different sides. Let's see. Let's go ahead. Let's go ahead and do number. I'll come back to number 2. Let's do one. Yeah. Let's go ahead and do number 7 on page 11. Well, actually, your page numbering might be different. If you printed out the copy from Schoology, your pages might be a little off. If you got it in class, then it should be page 11, but we're on number 7. Okay, so that's what we're doing here. All right, so let's do number 7. So for this one, we have to factor first. Okay, notice that the x plus 4s are common, so you can cancel those out, which means since x plus 4 canceled out, you set that equal to 0. You got x equals -4 for the x coordinate of the whole. To find the y coordinate of the whole, now you're going to take -4 and you're going to plug it in to the reduced fraction. I keep doing that. This should not be x plus 4. This should be x minus 4. Sorry, I canceled out the x plus 4. The x minus 4 is still there. You type that in, or you plug that in rather, and you're going to get 1 over -8, or -1/8. So that's the location of the hole. Next, to find the x-intercepts, you look at the numerator, set it equal to 0. In this case, there's nothing to solve for, so there is no x-intercept. The y-intercept, you plug in 0 for x. So 1 over 0 minus 4, that's going to be -1/4. Vertical asymptote, you take the denominator that we have left, you set it equal to 0, you got x equals 4. Since the degree is linear over quadratic, or even when we look at it reduced, here it's constant over linear, you see the degree of the denominator is larger. And so for that reason, we have y equals 0 for the horizontal asymptote. Anytime the degree of the denominator is bigger, y equals 0 will be the horizontal asymptote. So that means there's no oblique. So now what does this look like? Well, we have x equals 4, and y equals negative 1/4 for the y-intercept. We do have a horizontal at y equals 0. Okay, and just based off of that information, oh, and I also have a whole -4, -1/8. So if I go to -4, -1/8 is a little closer to the x-axis. So just based off of this picture, you can kind of see that on this side we need to have something that looks like this. And now over on this side we don't have any information, but we can go back. You see how this asymptote factor is to the first power? That means these need to be opposite. So it's got to be something like this. Okay? And that's an example of where the horizontal asymptote is y equals 0. All right, let me do one that has an oblique. Yeah, let's do number 9. Okay. So if you go to number 9, okay, hopefully now as we do more of these together, you kind of get the hang of this. We're going to factor. So this will be x minus 2, x minus 1. There is nothing that will cancel here. And again, now we just find all the details. So x-intercepts. Look at the numerator. You set it equal to 0. You get x equals 2, and you get 1. The y-intercept, you plug in 0 into all the x's. So either do it here, or I would actually suggest going back to the original. If that 0, that 0, and that 0, all that's left is positive 2 over -4, which is -1/2. Vertical asymptote comes from the denominator. There's only one factor there, so that'll be x equals 4. And there is no horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. Anytime that happens, we have an oblique asymptote. Can't have both. So now how do we find the oblique asymptote? You're just going to go back to the original one here and either do long or synthetic division. Okay, and now this is set up for synthetic. Since we're dividing by x minus or x plus something, that's easy to do. So I'm going to do synthetic division right up here real quick. Remember, you take the what you're dividing by, you set it equal to 0, you got x equals 4. Now you write down the coefficients of the numerator. And then you just bring down the first number. And now you multiply 1 times 4. You get 4. You add that up. You get 1. And now you take this number times 4. You get 4. You add those together. You get 6. So 6 is the remainder. And here's the quotient. This represents 1x plus 1. The oblique asymptote is always just the quotient. Quotient only, not the remainder. The reason for that is because as x gets really, really large, if you actually wrote out what this would be, which is x plus 1 plus 6 over x minus 4, okay, this term essentially disappears. When you plug in super large numbers, really it's just going to be x plus 1. Okay? No hole. All right, so we have all our details. And now we're going to put them on the graph here. So we have x equals 2, x equals 1, vertical asymptote at 4, oblique asymptote of x, y equals x plus 1. This is just a regular line. So imagine, y-intercept of 1, a slope of 1 over 1. And so you're going to get a diagonal line that looks something like this. Okay. And what else do we have? We have a y-intercept of negative 1/2. And so based on what I'm seeing here, okay, I need two branches, right? There's one asymptote, so there's got to be two pieces to the graph. If there are two asymptotes, there's going to be three pieces to the graph. There's always one more than there are vertical asymptotes. On this side, the only thing that would make sense is for it to do something like this. It's got to hit the x-intercepts, and then it's got to come back and hit the y-intercept, and it's got to stay close to that oblique asymptote. Okay, and now over here, no x-intercepts, so this scenario would be impossible. Also, notice the degree of the denominator is larger, and the degree of the denominator is 1. Odd multiplicity means that these are going to be opposites. So if this is going down on the left, on the right it should be going up. And so that means we get something that looks roughly like that. Okay. So there's an example with a hole, oblique asymptote. We did. Hole was right there. We did one with just a plain one. Now let me go ahead. I'm going to go ahead and do number 4. So this will be the last problem I'll do with you guys, and then again, email me or if there are questions. But the last thing that we have yet to talk about is this scenario. Now, so far I chose examples where the graph would not cross the horizontal or oblique asymptote, but we did mention that it is possible. So I'm going to do one where it does and show you how you would check. Okay. Now, usually when you have quadratic over quadratic or cubic over cubic, that's the times that we're going to see the graph cross the horizontal asymptote. And so let's see why that is. Okay, so if we factor this one, you can take out a 2, you get x squared minus 4, so that's going to factor to x minus 2, x plus 2. And this is already factored. And I'll just fill out all the details. So we have an x-intercept of positive 2 and negative 2. That's from this factor and that factor in the numerator. The y-intercept, if you plug 0 into the x's, you get negative 8 for the numerator, and then you get negative 3 for the denominator, so it'll be positive 8/3. The vertical asymptotes are going to be x equals negative 3 and 1. Horizontal asymptote, since the degrees are the same, we got a quadratic divided by a quadratic. You take leading coefficient divided by leading coefficient. So you got 2 divided by a 1. So that'll be y equals 2. And that means there's no there's no oblique asymptote. And nothing canceled in this case, so there's no hole. So let's put these details down, and then we'll talk about crossing through the horizontal asymptote and where that would be. So positive 2, negative 2, those are the x-intercepts. Positive 8/3, that's 2 and 2/3 roughly, so that's up here. Horizontal asymptote is y equals 2. So that's right about here. And vertical asymptotes, we have one at negative 3. X equals negative 3, and also at x equals positive 1. Okay, I think I have everything else. And so I mean, you can kind of see it here. So you have an x-intercept here, and then the graph's it's smooth, so it's got to connect from here to there. So at some point, it's going to cross through this horizontal asymptote. Okay, so now how do we find that? So I'll go over here. So where does it cross? Here's what you do. You take the value of the horizontal asymptote and you set it equal to the equation. So you plug 2 into y, and then you set it equal to your function, 2x squared minus 8 over, I'm going to go ahead and multiply this out. That's going to be x squared plus 2x minus 3. Okay, so you're going to set those equal, and then you're going to solve. So first I would multiply by the denominator. You get 2x squared plus 4x minus 6. And that's going to equal 2x squared minus 8. And so you solve this equation. Notice the 2x squareds cancel out. And so now you have 4x minus 6 equals negative 8. You can add the 6 over. So 4x is going to equal negative 2. And then you divide by 4 and you get x equals negative 1/2. So at x equals negative 1/2, so right about here somewhere, that's where it crosses through the horizontal asymptote, okay? And so, let me use red. In this section, it's going to look much like a cubic or a tangent graph, if you remember those. And now, based off of that, we should be able to fill everything else in. You just got to make sure you hit all the points that you need to hit. The multiplicities of the vertical asymptotes are both odd, to the first power for the x plus 3, to the first power for the x minus 1. So this is another case where they always are heading opposite directions. So if we're heading down on the right side of this first one, then we should be heading up on the left side. And so that means we're going to have something that looks roughly something like that. We've already filled this one in. Same with this one. If this one's heading up on the left, and then on the right it should be heading down. And you can see right there, that makes sense because now it's going to go up and hit 2 and then do something like that. Okay, so that's an intro to graphing these rational functions. Again, just let me know if there are any questions via email or when we check in later in the week. Thanks.